allocated for the seminar. And today our speaker is Sachindra Dahal, in short Sachi. He's a PhD candidate in our group, and he's working with Professor Rissler, and his research topic is about, and today his presentation title is about the crack development and strain responses of continuously reinforced concrete pavement, CRCP, and I believe he's going to present us some of his field measurements that they were working on for some time for tollway roads. I'm expecting this to be a quite interesting presentation. Let's just give him a warm applause. Right, yeah.
So I'm Sachindra, and I'm presenting about re-engineering CRCP. I work with Professor Rissler, as he mentioned, and let's start. So I'll begin with some basic features of CRCP. CRCP is a concrete pavement that has continuous reinforcement, longitudinal reinforcement. And one of the features is we don't manually make any joint in CRCP. So the CRCP has cracks, random cracks at regular interval, and these cracks are very tight. And another feature of CRCP is restrained at the end. So we have an end treatment that restrains the movement of the concrete pavement due to any temperature variation or drying shrinkage. And one of the main benefit of CRCP is it has a potential of being zero maintenance pavement if it is designed and constructed properly. That's the main thing. So this is the basic schematic of CRCP. We have a lot of longitudinal reinforcement. We have crack spacing, the naturally occurring crack that has spacing of about 1 to 2 meters. And we have some longitudinal joints, but no any man-made transverse joint. So there are a lot of steels used in CRCP, and the longitudinal reinforcement bar size, it depends from number 6 bar to number 7 bar, depending upon like how much reinforcement we want. We usually go from 0.6% to 0.8% of the cross-section area. The steel content is that much. So that would mean that we have around 22 to 26 longitudinal steel rebar at 6 to 7 inches spacing in a lane. So the longitudinal reinforcement can be black steel or epoxy coated. So this generally depends on whether what part we are in. Like if there is a lot of uses of salt, then it's generally epoxy coated. Otherwise, even the black steel is used. And we support this longitudinal bar in a chair that supports a transverse bar. And the transverse bar that we use is usually number 4 bar at 4 to 5 feet spacing, usually 4 feet spacing. So there is no man-made joint. So there are cracks that naturally occur because concrete, when you construct a long concrete, it cracks. And there are crack spacing of like 1 to 2 meter crack spacing. And ideally, this is the ideal case that we would want a CRCP to crack like this, like 1 to 2 meter crack spacing. And crack width is very tight. It's less than 0.5 millimeters. And if we have these sort of ideal case, then it performs very good, and it depends on the design and how we construct the CRCP. So this is the information. So end restrainment is another important part. So we don't want the CRCP to move a lot. So we restrain it by providing higher steel content at the end. So we restrain the movement of CRCP. So that styrofoam over there is the expansion joint. That's the joint between. So this is an approach slab. The slab that's already constructed is the approach slab, and we have tied that to CRCP to restrain the movement. So let's talk about some of the advantages of CRCP. So the main advantage is it has very long life, over 40 years of exceptional performance. And there is minimal maintenance because there is no man-made joints. So there is no use of sealant or other maintenance costs related to any joint. And the cracks are really tight. So it provides better load transfer because of aggregate interlocking. And it provides, as the crack is very small, it provides smoother ride. And LTTP data shows that smoothness is maintained even after 20 years of service in high volume traffic. So it's exceptional that CRCP provides this. And the other thing is at the end, like any pavement comes to an end of its design life. At the end, it provides a very good, suitable platform for asphalt overlay at the end, or any concrete overlay at the end of the life. But like CRCP has some disadvantages. Otherwise, we would use CRCP all the time. So some of the disadvantages are like it has higher initial cost, which is associated with the steel used, steel reinforcement, and the placement. So not just steel reinforcement, it's very manual or labor intensive because you have to put the steel in the right location and right amount of steel, right location. So it's very expensive. And another thing is design is very critical. So we need to provide proper thickness, selection of the base layer, whether we want to use a cement-treated base or microsurfacing over cement-treated base, or asphalt and cement-treated base composite, like 2-inch WMA over 4-inch CTD, something like that. So the selection of base layer affects the performance of CRCP. Another thing is erodibility of the base layer. So we want to have a layer that doesn't erode easily so that there is no stress concentration and it performs good. And proper material selection. So concrete material, so the performance of concrete might have some durability issue related to the material used in concrete. So that is a very key factor in giving a proper design. So all of these might lead to a disadvantage if we choose anything wrong. And higher level of construction training is required for the construction. So these are some common distresses that CRCP face. One is punch out. So when we have two transverse crack, closely spaced transverse crack, and a longitudinal crack goes through that two transverse crack, then we have a punch out. We have a delamination in CRCP, which occurs generally at the level of the steel reinforcement. Spalling of the cracks, we have a lot of cracks, so if we don't have proper material selection, we might face the problem of spalling. Pumping along the longitudinal A's, longitudinal cracks. These are some of the CRCP distresses. So the performance of CRCP usually depends on the crack spacing. Crack spacing is this distance between any two cracks, adjacent cracks. And crack width. Crack width is how wide a crack is. So these two factors are the main factors that determine the performance of CRCP. And the foundation layer, how erodible the layer is. In MEPDC criteria, the punch out, so failure criteria is 10 punch outs per mile or higher than 172 inch per mile IRI. So some of the key design input for CRCP in MEPDC is slab thickness, which is around 80 to 90% of JPCP. So this is one of the factors. So we have slab thickness that's around 80% of JPCP, and we have added steel on top of that. So that increases the cost drastically. And we have base type, as I mentioned last time. We have steel content, whether we want to use higher steel content or lower steel content. At what depth do we want to include that steel bar? The type of soldier, whether we want to use an asphalt soldier or concrete soldier, tied or untied concrete soldier, that affects the performance of CRCP. The climate, whether we are constructing it in Texas or California versus Illinois or Wisconsin. Construction month would affect the setting time of the concrete. I'll briefly discuss about that. So if we construct, I'll briefly talk about that when we reach to that section. So other concrete properties, strength of the concrete, shrinkage in a concrete, elasticity, thermal property, which is governed by the aggregate used in concrete, and the width of the lane, whether we are using 12 feet lane or we are using widened lane, which would be 13 to 14 feet concrete lane, traffic, and reliability like any pavement. So this is the existing model of crack spacing. So it depends on various interaction of various factors, like slab thickness is involved, the steel content and the depth of the steel, the concrete properties, the steel and concrete interaction, how do they interact with each other, the base friction, how the base provides the friction. All of these factors affect the crack spacing. And the crack width of the concrete for the existing model is dependent on concrete property, how much it shrinks, what's the elastic modulus of the concrete at that point, the thermal property, which depends on the aggregate, the climate where we are constructing, the construction time, whether we are constructing it during a hot weather or during a cold weather, concrete and steel interaction, concrete and base interaction. These all factors affect the crack width modeling. So why would we need to further study CRCP is there is a complex interaction of material, steel, and base friction that result in crack that are randomly generated, crack and crack width. And the cracks allow ingress of debris or some chemicals that has potential of causing some durability issues in concrete and deteriorate the concrete pavement. So we would want to find a design that has higher degree of predictable crack spacing and width. So we want to predict the crack width and spacing more accurately than it is now. And another thing is reduce the cost of CRCP so that the initial cost is not as high as the JPCP. It's not much more higher than JPCP. So overall research objective for this presentation is like we want to see crack spacing and width development for different amount of steel content. How does crack develop at lower steel content versus higher steel content? How does lightweight versus virgin aggregate? Lightweight is internal curing. So it's a feature in which an aggregate absorbs the water. It's a fine lightweight aggregate. They absorb the water and they release the water when the hydration reaction is going on. So how does the inclusion of lightweight aggregate affect versus virgin aggregate? The type of base, using composite base, a microsurfacing, or just using CTB base, how does it affect the friction using fibers? All of these, role of all of these in the performance of spacing and width. And we also want to see like whether we can reduce the cost by lowering the amount of steel and adding fibers to it. How does that affect? What's the role of active cracking? Active cracking is when we want the cracks to not be random. So what we do usually is, or sometimes is, we provide a notch at different spacing. So that notch would decrease the thickness, and it would be around 2 inches notch, and we would want the crack to go through where we want it to go instead of going or being formed randomly. So for this presentation, I'll also be referring like internal curing and lightweight aggregate. These will be interchanged, these terms. They mean same thing. So what we are doing right now is we have 2 parts in this project. So we have a field section here in Atlas Yard where we have 2 500 feet long continuously reinforced beams, which is exposed to environment, and it's instrumented with thermocouples, strain gauges, relative humidity gauges. And we have an experimental test section in Elgin O'Hare Expressway, which was constructed this last summer by Illinois Tollway. So each test section in Tollway is divided into further different sections, which are like exposed to real environmental conditions and real traffic. And these are also instrumented with strain gauges and relative humidity. So this is what we are monitoring. We are monitoring crack spacing with internal strain, temperature, moisture, end movement. These are the things that are being done in field, and the material properties are being done in lab. So we are doing tensile strength of the concrete creep, zero stress temperature, coefficient of thermal expansion, and these factors, these 4, internal strain, temperature, moisture, and end movement, these are being instrumented and monitored. So let's switch to instrumentation of the concrete pavement. So we have sensors that needs to be embedded inside the concrete, which are connected through wire to a node that captures the data locally and stores the data locally. These nodes then transfer the data that is stored to a data logger wirelessly through radio frequency communication. And these data logger collect the data from all the different nodes. So one data logger can control large number of nodes. It depends on what node we are using, strain gauge, temperature, what's the sampling rate. And these data loggers are then connected to internet, through which we can use the software or the cloud and access to the data remotely from anywhere. So that's the flow of information using the instrumentation. So some of the sensors that we used was static strain gauge, dynamic strain gauge, relative humidity sensor from Sensiron, thermocouples from Omega. So they are placed in chairs or trees. That's what we call thermocouple trees or relative humidity trees. Strain gauges are connected to a V-Link, which is manufactured by Lord Microstrain, and we have used Arduino for relative humidity gauge. And the thing is, like, each of these nodes can be individually powered. So powering any instrument in field is a very big challenge, and this provides us that. So these are the data loggers, and Raspberry Pi is another Internet of Things that we have been using to communicate with Arduino and collect the data from relative humidity sensors. So the gateway uploads everything online, and we can go online and really see all these data real time. So the unique feature about this instrumentation is each node collects the data locally, and we can power each node individually instead of having a central power supply system. And as these nodes and data logger communicate wirelessly, there is significant reduction of wire, which we will see in some of the slides later on, how far all these nodes and the data logger are. And application of Internet of Things devices, they're economical, and they have potential of increasing the density of sensors in future. We can use a lot of sensors in a very economical way. So let's shift gear to the beam section in here, atrial. So we have two 500 feet long beams with different combination of material steel. Let's start by this. So we have two beams. Each beam is divided into 4 different sections. So the difference is one of the beam is higher reinforced 0.8%, the other is 0.58%. Then different sections have lightweight aggregate or virgin aggregate in each of these beams. At the end, we have provided active cracking to see how active cracking helps in the development of the cracks. And for the lower steel content, we have kept fiber in 2 sections to see whether we can find closed cracks that form in the lower steel content section. And the active cracking is done every 6 feet for up to the 60 feet from the end of the beams. So it's a beam that's 15 inches wide and 10.5 inch in depth. So the cover of the steel is kept at 3.5 inches from the top and the side of the beam, which is usually the typical depth at which we keep these beams, keep this reinforcement in CRCP. And we have number 6 and number 7 bar like in CRCP. So we have restrained the end movement like CRCP has by drilling L-shaped anchor or rods down to the base and prevent the movement of or try to prevent the movement of the CRCP when it shrinks and expands. So it provides the restrainment. So when we observe the crack development over time, so we have number 6 and number 7 bar beam, and then if we look at crack that develop over time, we see that number 7 has slightly more number of cracks than number 6 bars because higher steel content restrains the concrete more. But the trend is similar in both of these. There is not much significant difference in the rate at which it develops, the crack. And at like day 300, the crack spacing is around 3.1 feet in number 6 versus 2.8 feet in number 7 bar. And if we look closely in number 7 bar, the beam is divided into 4 different sections, out of which 2 is lightweight aggregate and 2 is virgin aggregate. So if we look closely, we can see that the rate at which lightweight the crack develops in lightweight is lower than the rate at which the crack develops in the virgin aggregate. So lightweight has less number of cracks initially, but eventually it will come and catch up with the virgin aggregate. If we see the trend in number 6 bar, the bar with lower reinforcement, we see the similar trend. Lightweight has less number of cracks initially, and eventually it will come and catch up with the virgin aggregate section. Now, if we see the crack spacing distribution, what we observe is in number 7 bar, which restrains it more, which restrains the concrete more, has closely spaced cracks versus the one in number 6 bar, the lower reinforced bar as expected. So the key observation that we have made till now with respect to crack spacing in these beams are lightweight has lower number of cracks initially, but they come up and catch up with the virgin aggregate. And higher steel content has slightly more number of cracks, but they have similar trend as lower steel content. And for the active cracking section, the saw cut section, we have noticed that the crack doesn't initially propagate through these sections. They take quite some time to propagate through these sections, although we provide notch after a few hours of construction. For the strain thing, so let's see this case in which we have an original length of a concrete, any concrete. If we expose it to environmental loading, change in moisture and temperature, it changes if it is not restrained, it wants to change it changes the length of the concrete based on the environmental loading. So that's what we get, the total strain, stress independent strain. But if we provide some restraint to it, it cannot shrink as much as it wants to. So the restrainment provides some friction. So we have a residual strain over there, which is less than the strain that we would have got if it was not restrained. So the zero stress temperature, as I mentioned early on. So we have a typical hydration curve, concrete hydration curve. And so initially concrete is plastic when we place the concrete and it starts surrounding the strain gauge. So there is not much meaningful data that comes from the concrete because it doesn't have any stiffness. It's not strong enough to provide any strain. So eventually the concrete sets and we find a zero stress point. So zero stress point is the point which there are different ways of finding the zero stress point and a lot of debates going on, but one of the method is it's after the peak of heat of hydration. And that's the point which we assume as a zero strain for all the different concretes, and then we start the measurement of strain from that point. So any strain measured by the gauge is affected by various factors like a concrete has an elastic strain, creep, shrinkage strain, thermal strain. So the strain gauge measures the total strain of the value, and there are strain dependent and strain independent strains that also affect the total outcome of the strain. So usually the unrestrained strains are found from the samples that we make and take it to the lab and find the unrestrained or compute it from the concrete that's unrestrained. And we have elastic strain that depends on the stress and the elastic modulus of the concrete. So if we see some of the strain data for high steel and low steel content, what we can see is the blue line is the temperature. So we can see the clear fluctuation of the strain based on the temperature variation. So this is the data up to day 15. So we can see that below there, so the strain gauge has two crack faces that are on the sides. So initially, as there are fewer number of cracks, so we are measuring the strain in 45 feet effective section and 23 feet effective section. But as we move on with time, there are more cracks that develop over time, and they reduce the slab in which the strain gauge gives the measurement. So if we go up to like 180 days, the slab length, the effective slab length, or the distance from the strain gauge to the crack reduces drastically, and it comes down to around 7 feet or even up to 1 feet. So that means like the small section moves more. So we start seeing the more variation in strain over time from the strain gauge. So let's slightly move towards the instrumentation in the tollway section, where we constructed two different sections this summer. So test section 1 is completely internally cured section, or lightweight aggregate section. It's around 200 feet section. And section 2 is 1,000 feet section without any internal curing. The site is in west of O'Hare, 5 miles west of O'Hare. So this is a schematic of the first section, where the total length is divided into 5 parts. The hatched part is toll plaza, where tollway collects the toll. And this is the section 2, which is divided into 2 parts. This is the controlled section. So instrumentation of CRCP. So we put the instruments in chair, and as the slip form paver, like it has massive amount of concrete flowing through it, and it has higher force that tries to tilt, and the orientation of strain gauge or any gauge and location of those gauges are very critical to get the correct data. So what we usually do is we cover these gauges using concrete prior to the slip form paver moves on top of it. And that's the picture of instrumented CRCP after the paving is done. So the advantage of wireless thing is the data logger box as shown in the right figure, and the node is the wireless node that locally collects the data. It's around 520 feet. In this case, in this picture, it's around 520 feet apart. So we don't have to run wires through that. So each individual node has around 15 sensors that are connected from the node box. The wire goes under the shoulder to the concrete pavement. And we don't have to connect any wire from that to the data logger at least. So that saves a lot of wire when we have 2 sections that are 2,000 feet, and each section has around 15 sensors in it. So the data logger consumes more power, so we have provided a solar panel for the data logger, but all the other nodes, they are individually powered by batteries. That figure on the right shows the complexity of the box in the node. So each of these nodes are powered by small D-size batteries. And the picture on the left shows the wireless node box with traffic running. The road has already been open to the traffic. And again, like field instrumentation is not always fun. We see a situation where all of our node, so we have to go and change something, check the battery level and all the other things, and we have a situation like this where all of your site is inundated. So let's start seeing what we found in the initial. These are the preliminary results. So for a CRCP pavement to be stabilized, it needs around 1 or 2 years. And again, like this result is from the initial behavior of CRCP that has not undergone any freeze and thaw cycle. Freeze and thaw cycle would create more number of cracks. So up to the date, like 180 days. So these two internally cured and the virgin section that's not internally cured, they were constructed in 2 different times. They are slightly apart, like 1 mile apart. So we have different days for which we have done the crack spacing and compared the cracks. So we can see that for non-internally cured section, we can see the cracks are more closely spaced than the internally cured section for early age. And what we can see, another thing, if we see the crack width, like how wide the cracks are, what we can see is the no internally cured section or the section with virgin aggregate has wider cracks. So it has closely spaced cracks and it has wider cracks. So versus the behavior of internally cured section. And another thing we can see is crack spacing for low and high still. There is absence of closely spaced crack in low still versus high still. There is more restrainment, and we see a lot of cracks in regular pattern. So the other crack width, if we compare high steel versus low steel, how is the crack width doing versus crack spacing? What we see is the lower steel content has more wider cracks. The lower steel doesn't provide as much restrainment as higher steel, and higher steel shows more tighter cracks. And the crack width is essential for the performance of CRCP, its potential for damage in concrete or concrete pavement. So earliest key observations till date is internally cured as closed cracks. There is higher percentage of wider cracks in non-internally cured section, and higher steel content as tighter cracks as expected. And as we observed in the Rantoul beam, what we can see is we have provided notch in the ends of the CRCP segments, and we have not seen any cracks. Till date, only one crack has propagated through the notch, so it's still taking long time for the crack to propagate through the active cracking section. So in summary, the performance of CRCP depends on crack spacing, width, foundation layer. The study focuses on the rate of crack development and crack width control. Internally cured CRCP is a very good option for controlling the crack width and spacing, as we saw from some of our early observation. And it initially creates lower number of cracks that are tighter, so it has very good potential in future. And higher steel content, although it's expensive, and it has slightly higher number of cracks, it also provides tighter crack. And active cracking is not doing as much as we were expecting. Like we expected most of the cracks to pass through active cracking, which we have not seen yet. So for future, like we can try the layer with CTB only. So we have used interlayer right now and microsurfacing. We can use CTB layer. We can do more studies in internal curing. There has not been a lot of use of internal curing in CRCP. We can do more research in this and find using the fixed steel content, using active crack at the end terminal. End terminal restrains the movement, and then we generally see lower number of cracks at the end. So we can try to use more aggressive way of active cracking at the end to provide more cracks at the end. So this is the acknowledgement. But so this research has different universities involved and agency. TOLO is the main funding agency. We have Professor Dan Jollinger from Texas A&M, who is also involved in the project, and Professor Jason Wise and Armin from Oregon State University. Thank you.
Great. Questions?
I just had a quick question about the test sections. Thanks for your presentation. What was the year that you did this again? Was it earlier this year or?
We constructed it in June, July.
Are there plans for later, like going back next year, or like how
Yeah,
long is the data collection?
We'll be collecting data for about about a year, and then we also have another test section that we'll be constructing next year, and most probably other section which are in preliminary stages of research. Like we have other plans for other ramp and everything, CRCP in Tollway.
And with the wireless system, do you have to do a lot more kind of maintenance or?
Maintenance, till now, like we have not done any major maintenance. So one of the main reasons we used that wireless system in Rantoul was to see how it performs. And it has been about a year, and we don't have any major issues of using it. So the good thing is it stores the data locally, and there might, due to some environmental condition, there might not be radio frequency communication between the node and the data logger. So what data logger does is, as soon as it keeps on repeating, like asking for the data from all these nodes in like 5 or 6 minutes. So if there is any loss of communication, and if they come back to communicate with each other, then they will get all the data back.
How do you measure the crack width?
We have crack comparator, as I showed in the first slide. So it's done manually.
Manually, okay.
Yeah, it's manually. It's not.
That's when I thought you were doing this with one of the
Fancy.
sensors, okay.
No. So we manually measure the crack width. So it's the most subjective part.
Okay.
Because like we have 200, 300 cracks that we have to go and manually measure the thing. And the crack width changes on different segments of the lane. So usually crack widths are wider towards the A's and it starts getting smaller in the middle. So we find a location where approximately like that represents the overall crack width, go there and measure the crack width.
Are the sensors recording the information all the time continuously, or they have some kind of a system they wake up to record
Yeah.
and then they sleep?
Yeah, so they wake up every 15 minutes to 10 minutes. It depends on like what sensor we are talking about and power requirement. If we use higher frequency of sampling rate, then it consumes more power. So to balance that, so strain gauges and thermocouples we have done around 10 minutes. For dynamic strain gauge, we have not activated it, but another good thing is we can activate the dynamic strain gauge. We can make the dynamic strain gauge act as a static strain gauge and collect data every 15 minutes. And another thing we can do is we can go online and start a trigger in which it starts recording for 15, 20 minutes at higher frequency like 512 or 2000 kilohertz, 2 kilohertz. It's sampling rate, and then so it basically sleeps for most of the time to conserve the power, wakes up every 15 minutes, collects the data, transmits the data, and goes back to sleep again.
And about the installation, I saw that you have really a big chunk of materials that you put prior to slip form, places the rest of the concrete. But is there any concern with the amount of, the interaction of that material that you put for protection and the rest of the concrete?
So you mean for the protection of the sensors?
Because there's a lot of material that you put it in there to protect your sensors, right?
Let me go to that.
And then you pave it after
let's see.
so the sensor will be embedded in this initial part of material that
Yeah. So what we usually do is, so if we don't embed it, it overturns because of the movement of the concrete that's flowing through the slip form paver. So what we do is they put the fresh concrete from this side of this slip form paver, and the concrete gets distributed and labeled by the machine over there. So when we are about like 50 feet from the paver moves pretty fast for 50 feet. So when we are like around 50 feet from the paver, what we start doing is we get the same sample of the concrete, we put that concrete around these thing, and we try to make sure that all the sensors are in straight or like the position we want it to be and location where we want it to be. And so the paver, with the same concrete, the paver would come back to that location in about, I would say 10 minutes, 10, 15 minutes. So it doesn't affect drastically. So it starts setting slightly ahead or later than the concrete on the other side, but actually like it doesn't affect it too much because we already have that concrete takes like 5-6 hours to set, and then we are just putting a concrete to protect the sensor like 10 minutes, 15 minutes, and same sample from the same batch.
Other questions? So those I forgot what was the name of the failure when two slabs.
Punch out.
Yeah, they are usually happening at the approach slab and with the CRCP, right?
It might happen, but the thing is, when there is an approach slab, there is an expansion joint over there, which allows movement of CRCP. So we don't usually see a lot of cracks going near the approach slab. So a lot of CRCP is mostly restrained on the middle portion. So that portion where there is expansion and contraction, we usually do not see a lot of cracks in about 100 feet from the expansion joint. So it usually occurs in the middle than towards the until and unless we have some problems with erosion where the base erodes.
Thank you. There is no any other questions. Let's just give him another warm applause and then. A good presentation. Thank you. Pizza is here.